Looking at some notation, the line integral over c with a little circle over the integral symbol of p dx plus q dy indicates a positive orientation for c. Now the positive orientation is required for Green's theorem, but not just in general for line integrals. So that little circle sometimes is used. Sometimes the little circle has a little bitty arrow on it, but anyway, there's the little circle business. Also, the positively oriented boundary curve C that bounds D can be written as what looks like partial D. So we can write the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y dA. It can be written as the line integral over what looks like partial D of P dx plus Q dy. And just to really bring this home and connect it with the previous section, this equals f of x2 y2 minus f of x1 y1 if we have a vector field f, which is given by pi plus qj, and the vector field is the gradient of a function f. Now, the fundamental theorem of calculus part 2 says that the integral from a to b of an f prime of x dx is equal to f of b minus f of a, and we know that f is an antiderivative of f prime. Here's what we have in both of these cases. On the left-hand side of the equation, we have an integral involving derivatives. On the right-hand side of the equation, we have an original function, and it's got values only on the boundary. For an interval, the boundary is comprised of a and b, right? Just the points. Now for our region D, the boundary is our curve C. And when we view it this way, Green's theorem essentially becomes the fundamental theorem of calculus for double integrals. I feel like I got all dramatic there. Well, this is dramatic. In practice, we can evaluate whichever integral, either the single one or the double one, is easiest to set up and integrate. For our first example, we're actually going to do it both ways. We're going to evaluate an integral directly, and then we are going to use Green's theorem. The integral is the integral over the positively oriented curve C of y dx minus x dy, where C is the circle of radius 4 centered at the origin. All right, so to evaluate directly, what we need to do is parameterize C. So for the first one, part A, C is going to be given by r of t, which equals 4 times the cosine of ti plus 4 times the sine of tj. Quick mental check that that's positively oriented for that circle. And of course, to go all the way around the circle, we need t to go from 0 to 2 pi. At this point, go ahead and pause the video and finish up part A on your own. X equals 4 cosine of t, so dx equals negative 4 sine of t dt. Y equals 4 sine of t, dy equals 4 cosine of t dt. So y dx is equal to negative 16 times the sine squared of t, minus, because of the original integral, x dy is equal to 16 times the cosine squared of t. All that's being integrated with respect to t. T is going from 0 to 2 pi. Factoring out a negative 16, we end up with sine squared plus cosine squared, which equals 1. And so we are just integrating negative 16 dt from 0 to pi over 2 for a result of negative 32 pi. For part B, we were asked to use Green's theorem. So let's remind ourselves of what it says. Our line integral over C, the positively oriented curve, of p dx plus q dy is equal to the double integral over d of the partial of q with respect to x minus the partial of p with respect to y dA. First things first, C is a boundary. D is the interior. for the original curve, the circle of radius 4 centered at the origin, the boundary is the disk. And for this disk, we have that r will go from 0 to 4, and theta will go from 0 to 2 pi. We get to do that now because we're talking about a double integral, so I can have two variables. Comparing what's on the left-hand side of Green's theorem with the original integral in this case, we had the line integral over c of y dx minus x dy, and at this point it's kind of a matching game. P dx must then be y dx, which means that p is equal to y. Let me be a little more careful there. P of xy is equal to y. Back to our original integral, negative x dy is in the position that plus q dy holds. Therefore, q of xy must be negative x. To use Green's theorem, what we now need is the partial of q with respect to x, and then the partial of p with respect to y. Having identified what p and q are, we can now say the partial of p with respect to y is equal to 1, and the partial of q with respect to x is equal to negative 1. So the integral that matches the right-hand side of Green's theorem is the double integral over d of negative 1 minus 1 times dA. And for our purposes, we can factor out that negative 2, and then we have a double integral, and our region d is defined by this disk, where r goes from 0 to 4, theta goes from 0 to 2 pi, and we already know that dA is equal to r dr d theta. Evaluating this will give us negative 2 times 2 pi times 1/2 r squared evaluated from 0 to 4. 2's divide out. We end up with negative 32 pi as expected. At this point, folks, we could have said here, hey, this is a circle of radius 4, and so that's going to be 16 pi. We get the same answer.